Okay, so wait. I'll tell you what, I'll give you your problem set tomorrow and talk about it, so that way you have till next Wednesday. Because I feel like if I give you, I just have a feeling if I give you something else and make it do, you're gonna like, your head's gonna explode. So I'll wait till tomorrow. I won't pile it all on one day. All right, so we'll do that tomorrow. I don't teach balancing equations again. So if you're not good at that, hopefully you just get better through the year. Just throwing that out there. All right, here we go. Stoichiometry. Let's talk about what we know. Stoichiometry with limiting and excess.
Is it reagent? Reagent?
Reagent. Reagent. R-E-A-G-E-N-T-S. Reagents. Reagents. All right, what do we know about stoichiometry already? What do we know about, what does stoichiometry mean? Like math. It's mole ratios. Mole ratios. I use the analogy of making pancakes. That's what I always use in reagents chem. So if you have all your ingredients and it makes 10 pancakes, if you want to make 20 pancakes, what do you do to the ingredients?
Double it.
Right. That's stoichiometry. That's stoichiometry. All right. Let's use a simple example. Let's make water. So we have H2 plus O2 yields H2O. What type of reaction is it? Synthesis. Simple reaction. Go ahead and balance it. I get to use my new magnets. I'll use blue and red. Blue is so nice. Okay. So we'll go H2 and O2. Now let's switch. No, they didn't have any of those. All they have is red, green, yellow, white, and blue. It's still pretty cool. All right. Okay. All right. Tristan, we balanced it, right? What do you got?
2 H2.
2H2?
Yep.
And what?
2 H2.
All right, good. All right. So our mole ratio is 2 moles to 1 mole to 2 moles. All right. Okay. All right. So let's say each one of these is a mole. Here's 1 mole, here's 2, there's 1 mole. Now I need one of those. What's the word excess mean again?
There's a leftover amount.
Leftover. What's limiting mean?
There's only a certain amount.
Limiting is completely used up. Excess has leftover. So now, use your brain. I didn't mean that like sarcastically. Like, try and figure this out. If you have 2 moles of this and 1 mole of that, it makes 2 moles of this. Which reactant is limiting? Which one is excess? Just by looking at the magnets. Don't say it out loud, think. So which one is going to be completely used up and which one's going to be excess? trick question. I probably shouldn't trick you right off the bat. I'll make it easier. I'll make it easier. I'll make it easier. Okay? Let's throw another couple on here. And now what I'm going to do is I'm going to get rid of the water. Now, what I want you to do, try and do it in your head. If you want to draw it, go ahead. If these 3 particles or moles of hydrogen and these 3 particles or moles of oxygen react to form water, which one of these is going to be completely used up and which one's going to have particles left over? So make the water and see what's left over and what's not. The one that's left over is excess. The one that's not is limiting. Think you got it? Think you got it? Everybody's got it already?
Mm-hmm.
Trevor, how many water molecules can I make from 3 moles of each?
Make 3.
Make 3, right? So if I take 2 H's and 1 O, if I take 2 H's and 1 O, and then I take 2 H's and 1 O. So who's limiting?
Oxygen.
This is limiting. This is excess. Why?
Because there's leftover.
Because it's left over. Write that down. What do I keep doing with this thing? So H2 is limiting, and O2 is excess. That makes sense when I use the magnets. Like you can see it, right? Okay. So you have to be able to now see it in your head, because obviously the problems aren't going to give you magnets, or they're not going to give you, sometimes they can give you particles, but a lot of times they just give you numbers, all right? So this is the whole concept of what limiting and excess means. Whenever you have a reaction, one of them is completely used up, the other one is left over. Now sometimes it's a perfect ratio and there isn't any left over, but that's extremely rare. All right, so using the same, well, actually let me write this down here. The limiting reagent / reactant determines the amount of product produced. So, this is hard for students to get used to, but from this moment on to the end of the year, anytime there's any question involving a chemical reaction and you want to know how much product or how many products are produced or how much product is produced, you need to find limiting. You're going to be sitting here in April, and we're going to be going over something, and some of you are going to forget because whatever the answer is going to be based on limiting, and you're going to be like, oh, I forgot to find limiting. You always have to find it. So any chemical reaction, the rest of the year, if there's moles, grams involved, and you want to know the amount of products, you need to find the limiting. Why? Because all of this is all of that, right? So this is excess. So we can't use this ratio. We can't use the 1:2 ratio because we don't know how much of this is being used. So we don't even mess with it. We know all 2 moles are going to be found here. So we can use the limiting ratio. If you're confused, that's fine. We're going to do a sample problem. But this is really important to remember. You need to find limiting. You have to find the limiting. I'm going to show you how to do it with numbers instead of magnets. Okay. All right. Let me give you another example, just out loud here. You guys like peanut butter and jelly?
Yeah.
I do too. I eat probably, let's see, at least 7 a week. 8 maybe.
What? That's so much.
Yeah. No, maybe like 6. Anyways, Okay, so let's say we have an unlimited amount of bread. All right, and we have a little tiny jar of jelly. So I don't like to use a lot of jelly, just a taste, just a little taste. And then a ton of peanut butter because I eat peanut butter about like a gallon. Okay. So we're making peanut butter and jelly sandwiches. Which reactant's going to run out first?
Jelly?
Jelly, by far. So the analogy here is this is limiting, this is excess. The number of sandwiches we can, assuming we have enough bread for whatever, as much bread as we need. So the bread's kind of like a constant. The amount of, or the number of sandwiches we can make, right? If these are our reactants and here's the sandwich, I don't know how to, there's our sandwich. Okay. That's a piece of bread. So it's like the top view of the sandwich. Anyway, the number of sandwiches you can make has nothing to do with the amount of peanut butter because you essentially have unlimited. It's like a super excess amount.
Technically, if you put like a lot of peanut butter.
Just, can you go with the
Peanut
analogy?
butter can
You
run
know
out
where I'm
first.
going with this. As soon as the jelly runs out, you can't make any more sandwiches. Assuming you can't go get more, okay, just stay with me. All right? So the analogy is, this is your limiting. So it's important, this is a really important concept. I'm joking around, having fun or whatever, but it's really important to relate this to the examples we're going to be doing. That once the limiting runs out, the reaction stops. That's how chemical reactions work. When this reactant runs out, you cannot get any more product. That's the point I'm trying to make. So the amount of your products is completely dependent upon your limiting. It doesn't matter how much of this you have. Does that make sense? I'm just
Yeah.
trying to give you an example of just something you would see, right, to make sense of it. Again, gasoline. When gas runs out, car stops. You have plenty of oxygen, it's the gas that matters. So limiting is what really drives the reaction. No pun intended. All right. Here we go. We're going to start out with something simple here. Oh, and I'm kind of assuming, sorry, probably, you shouldn't do that because of that phrase, but I'm assuming you guys can do the ratios. Maybe we should do one quick one to practice. Let's do one quick one to make sure you're familiar with the whole ratio stuff. All right, so the decomposition of potassium chlorate. So we're not going to do a limiting problem yet. I'm going to do one just review question with you. So you have KClO3. It decomposes into potassium chloride and oxygen gas. Why don't you put this on your reaction sheet? This is a pretty common reaction.
For like.
That sheet I wanted you to keep like in your folder or notebook that says,
No, I got that. Okay.
oh,
You want us to write like that or?
yeah,
say
this reaction, and then we're gonna balance it.
Okay.
It's just one you should have memorized. You should know. I'm just using this again as practice or review. Then we'll get into the limiting stuff, and that's going to be it for today. I know you've been sitting a lot here today, taking notes sometimes. This is how it goes. All right. Anyone balance it yet? You look at the oxygens, that kind of gives you a hint. Next number they have in common is 6, right? So 2 here.
2,
2, 2, 3, right? All right. So now again, just a quick review question here. How many grams of KClO3 are needed to produce 2 grams of oxygen, 2.0 grams of O2. So how many grams of KClO3 are needed to produce 2 grams of O2? You cannot use grams in mole ratio, so you're going to have to turn the 2 grams of O2 into moles first, because you have a 2 to 3 ratio. So what that means is I need 2 moles of potassium chlorate to produce 3 moles of oxygen. So I know I need 2 moles to make 3 moles. The question wants to know how many grams to make 2 grams. So the ratio is 2 to 3, but the unit, you gotta get the units all the same, right? So you gotta convert this to moles, then use your ratio, and then convert back to grams. So I'll give you a couple minutes here while I pick this up. We should say hi to Skylar. Hi, Skylar. Say hi to Skylar, everybody. Look how happy Ben is. I hope you're feeling better, Skylar.
Oh, she actually doesn't watch these.
I hope she does. She's going to be pretty far behind. State-of-the-art technology. I have a iPad stand with no cards holding it up. What? Just, keep working. Stop talking. Even though I started that. Sorry.
Yeah.
So 2 to 3 mole ratio. Convert your grams that they give you to moles. Work backwards and then convert it to grams. I usually snack around 9:30. I'm a little hungry today. Okay, we ready to roll?
Oh my god.
Do we have answers?
We're all gonna say our answers and you're gonna see how crazy, like.
Go.
Okay, I got 10.162.
I got 5.075.
I like that one. 5.08.
Ah.
5.08. Okay, here's how we do it. Okay, and then I want to get you a limiting example before we get out of here. All right, so we got to turn this to moles. 2.0 times 1 mole over 32 grams.
Yeah.
You only used 16, didn't you?
Oh, I used 32.
Okay. So grams cancel. So 2 divided by 32, I got 0.0625 moles of O2. Now I'm going to use my mole ratio. So I have 2 to 3. So here's my KClO3. Here's my O2, right? Is X to 0.0625 moles. So I still do proportions sometimes, just because I like that. It makes sense in my head. You can actually do this work just like this, but I like to do these this way. Hopefully you're okay with that. So I know it's a 2 to 3 ratio. So 2 moles produces 3 moles. Well, how many moles do I need if I only want to make 0.0625, right? I don't want 3. I want 0.0625. So I cross multiply and divide. So I need, this number's telling me how many moles of this I need. I don't need 2. I need way less than 2. I need 0.04167 moles of KClO3. So I need 0.0416. So 0.04167 moles of this will produce 0.0625 moles of that. Why? Because that's a 2 to 3 ratio. Now, it's asking for grams. So all I do is take this number and convert it to grams of KClO3 and you're done. So, let me just make some space here. So I take 0.04167 moles, multiply the molar mass of this, 122 I got. 122 grams per 1 mole. Moles cancel. 122 times that, I got 5.08 grams. So, that was a review. That's not a Regents question. So, if you had trouble, don't feel bad. That is an AP question. But I'm calling it review because we're not doing limiting or excess. It's just straight up stoichiometry without figuring that stuff out. So yeah, that could be on a test, or, that could be, but they're usually, most likely they're going to be asking about limiting and excess. So take this type of problem and then amp it up a little bit with the limiting and excess. Let me try and get one down here and start one with you, and then that'll be it. Don't forget those are due tomorrow, and then you got the other stuff at the end of the week. Okay. And let me know, talk to me today if you need to see me or you have questions. Just come up and talk to me at the end of class or something. All right, so there's that. Here we go. All right, so the formation of ammonia, N2 gas, plus H2 gas yields NH3. This is a really common reaction. I don't think you need to write it down. It's kind of like the formation of water. Like, you know that already. So this is just used all the time in books, worksheets, tests, stuff like that. So this is the formation of ammonia. It's called the Haber process. It's how ammonia is made, like industrially. On large scales, they have like thousands of moles. Anyways, balance it. Count.
Need 3H2.
3 here.
Yeah.
Okay. 2. here's the question. All right, if 42 grams of N2 gas react, so, okay, if 42.0 grams of N2 react with 5.00 grams of H2, find the following. A, find the limiting reagent or reactant. B, find the excess, not find the excess, that's too easy. Calculate the mass of NH3 produced. C, calculate the mass of excess reagent remaining. I think that's it. Yeah. So, given the mass of the N2 and the H2, we can find which one's limiting, then find the mass of NH3 produced, and then find the leftover amount. All right? But we'll stop. So just get that down. We'll pick right up with that. So tomorrow we'll go over the homework. We'll do this problem. I'll show you the demo, and the demo will be homework because it's just like this. All right, good work. You got a lot done.